서밋에 자리해주신 현장 참석자 여러분, 그리고 화면 너머로 참여해주고 계시는 온라인 시청자 여러분 반갑습니다. 저는 어제에 이어서 오늘도 사회를 맡아 여러분과 함께하게 된 아나운서 이소연입니다. 리더 서밋은 세계 수소 산업을 이끌고 있는 리더와 전문가들이 모여서 각국의 수소 정책을 비롯한 미래 전략을 공유하고 지속 가능한 발전을 위한 새로운 아이디어와 또 방향성을 모색하는 중요한 자리입니다. 오늘 어느덧 리더 서밋 2일차고요. 본행사의 마지막 날입니다. 오늘도 함께 끝까지 발표 경청해 주시고 이 수소 산업 발전을 위한 여러분의 지혜를 함께 모아주시면 고맙겠습니다. 자, 그럼 하이드로젠 호라이즌스라는 주제로 H2 컨퍼런스 2024 리더 서밋 2일차 토픽 2를 지금부터 시작하겠습니다. 자, 먼저 오늘 발표를 준비해 주신 첫 번째 연사분을 소개하겠습니다. 단국대학교 조홍종 교수님께서 자리를 해주셨는데요. 무대로 모시고 발표 함께 청해 듣겠습니다. 여러분 뜨거운 박수로 환영해 주시기 바랍니다.
네, 안녕하십니까. 전 단국대학교 경제학과에 있는 조홍종이라고 합니다. 저는 국가에너지위원이기도 하고요. CHPS 위원이기도 합니다. 넘기는 거 어떻게 해요? 제가 오늘 말씀드릴 내용은 산업의 탈탄소화와 수소 활용 부분에 대해서 말씀드리도록 하겠습니다. 제가 한글로 발표를 준비하는 바람에 그리고 한국 오디언스가 많아서 일단 한국말로 좀 발표를 드리는 점 양해 부탁드리겠습니다. 우리가 에너지를 써오는 과정은 한 산업혁명 이후로 석탄, 석유, 그리고 천연가스 이 세 가지 화석연료를 대량 사용해왔고 현재도 80% 정도를 사용하고 있습니다. 앞으로 전기로 이 에너지를 다 바꿔야 됩니다. 위에 두 개는 재생에너지와 원자력 발전입니다. 전기 에너지를 저희가 사용하는 부분은 앞으로 이 모든 화석 연료가 발전 부분에서 사용되는 걸 다 디카보네이션 해야 된다는 뜻이 되겠습니다. 근데 우리가 쓰고 있는 에너지의 파이널 그 컨섬션의 형태를 보면 포메이션을 보면 열 에너지가 50%이고 수송 에너지가 30%이고 전기 에너지는 20%입니다. 그러니까 전기를 청정 전기와 클린 에너지로 바꾸는과 동시에 앞에 나와 있는 80% 열과 수송을 전부 전기로 바꿔야 됩니다. 연력학 법칙을 어긋나지 않으면서 전기로 갈 수 있는 방법을 고안해야 되고 경제적인 방법이 있는지를 찾아내야 되겠습니다. 우리가 탄소 중립을 달성하기 위해서 넷제로로 가는 경로를 보면 제일 아래 그래프가 1.5, 중간이 2도씨, 그 위에가 2.5도씨입니다. 그러면 지금부터 2050년까지는 우리의 삶의 패턴을 완전히 변화하여 탄소 중립을 달성하기 위해서 CO2를 줄여야 된다는 것입니다. 그러니까 지금이 정점인지도 사실은 잘 모릅니다. 그럼에도 불구하고 우리는 앞에 계시는 플라스틱, 합성섬유, 비행기, 열로 만드는 철강, 시멘트 이런 걸 전부 디카보네이션 해가지고 삶의 패턴을 바꿔서 2050년까지 넷제로를 달성해야 된다라는 뜻이 되겠습니다. 매우 챌린징한 일이 될 것입니다. 그러면 우리가 지금까지 돈을 어느 정도 쓰고 앞으로 얼마 정도를 투자해야 되고 어느 분야에 투자해야 되냐를 보면 IEA 보고서는 215 트릴리언 달러를 2050년까지 투자해야 된다. 그 중에 대부분은 수요 쪽에 수요 감소 효율화를 위해서 투자함과 동시에 에너지를 서플라이하는 사이드에서 주요 기술적인 변혁이 일어나야 되는데 대부분이 하이드로전이거나 카본 캡처이거나 파워 그리드, 뉴클리어, 에너지 스토리지, 리뉴어블 이런 것들에 대한 투자가 대폭 그것도 천문학적으로 늘어나야 된다라는 뜻이 되겠습니다. 그러면 우리가 앞에서 말씀드렸던 기술의 특성에 수소 경제의 필요성이 있습니다. 수소라고 하는 것이 결국 자국에서 리뉴어블 에너지거나 어떤 전기가 남아도는 상황에서 탄소 중립을 달성할 수 있는 방안임과 동시에 에너지 안보, 에너지 세큐리티에도 도움이 될 것이고 신산업, 우리가 지금 수소와 관련된 전반적인 밸류 체인을 모두 육성하는 것에 한국이 굉장히 큰 강점이 있습니다. 그런 부분들을 전반적으로 다 가져갈 수 있다 이렇게 말씀드릴 수 있겠죠. 수소와 관련된 생산, 저장, 운송, 활용단에 이르기까지 모든 밸류체인에 대한 투자가 일어나야 된다는 뜻이 됩니다. 그래서 한국이 발표했던 100가지 탄소 중립 기술 중에 약 38가지가 수소와 연관되어 있습니다. 그 수소들은 보시다시피 수소의 공급, 무탄소 전원의 공급, 그리고 제로 에너지 빌딩, CCUS, 철강, 시멘트, 산업 일반, 친환경 자동차까지 전반적인 산업과 발전 부분 그리고 수송 부문까지 수소가 전반적으로 탄소 중립에 모두 기여할 수 있다는 뜻이 되겠습니다. 한국에서 지금 기술 개발과 R&D에 투자하는 자금들은 수소에 막대하게 투자되고 있습니다. 뭐 막대하다기보다는 많은 투자를 하고 있지만 앞으로도 더 투자돼야 될 것 같습니다. 다른 나라들도 EU도 그렇고 일본도 그렇고 오스트레일리아, 저머니까지 수소와 관련된 전반적인 밸류체인을 일으키기 위한 많은 노력을 하고 있습니다. 미국 같은 경우에도 7개 지역에서 수소 허브를 만들고 있고 독일 같은 경우에는 파이프라인을 북아프리카에서부터 생산된 수소를 끌어오기 위한 파이프라인 건설도 계획하고 있습니다. 그리고 리뉴어블 에너지가 남아도는 곳에서는 그린 수소를 생산하여 여러 곳으로 옮기는 방안들을 생각하고 있고, 그게 암모니아 형태로 결국은 움직일 수밖에 없습니다. 수소가 중요한데 가장 큰 단점은 마이너스 253도에서 액화가 되기 때문에 결국 이송의 방법이 쉬운 암모니아 형태로 합성하고 다시 가서 암모니아로 직접 이용하든지 아니면 수소로 크래킹을 해야 되는 상황이 되겠습니다. 한국의 상황을 잠깐 말씀드리면, 한국은 반도체 최강국 중에 하나입니다. 삼성 일렉트로닉스와 SK 하이닉스 두 회사에서 만들어내는 반도체, 특히 메모리 반도체와 앞으로 생산될 AI 반도체에서는 전기 생산이 핵심입니다. 전기를 어떻게 활용할 것이냐, 거의 70%가 스코프 2에서 반도체는 생산합니다. 그러니까 전기로 클린 룸을 운영해야 된다는 거야. 모든 아주 미세한 파티클들을 다 전기로 집진하고 잡아내야 됩니다. 그래서 전기를 얼마나 클린하게 공급할 수 있고 경제적이고 안정적으로 공급할 수 있느냐가 한국 반도체 산업의 핵심입니다. 그리고 이 오른쪽에 나와 있는 것처럼 다양한 다른 산업들, 특히 석유화학이나 철강, 그다음에 비철금속 등등에서도 스코프 1에서의 에미션 배출이 되게 많습니다. 에미션을 줄이려면 이게 결국 열 에너지를 사용하는 것을 전기 에너지로 바꿔야 됩니다. 근데 우리가 철강에서 철을 녹이려면 1530도 이상, 셀시우스 이상을 넘어가야 됩니다. 그럼 1600도까지 열을 내기 위한 전기 사용량은 막대할 것입니다. 우리가 또 아연 공정을 가면 900도까지 올려야 됩니다. 이런 열 에너지를 전기 에너지로 어떻게 바꿀 것이냐 하는 것이 기술 진보의 핵심이자 동시에 투자해야 될 분야라고 저는 생각하고 있습니다. 국내 석유화학 산업은 굉장히 그래도 원 단위에서 보면 클린한 공정을 가지고 있습니다. 다른 나라들의 화학 공정에 비하면 클린한데, 그러니까 이 말은 무슨 뜻이냐면 마지널 코스트를 줄이는 게 정말 어렵다는 뜻입니다. 그래서 전기화로 가는 데 있어서의 비용 증가가 발생할 수밖에 없습니다. 한국은 11차 전력 수급 기본 계획을 통하여 아직 확정은 안 됐지만 실무안을 통하여 수소 암모니아를 확대하기로 결정했습니다. 10차 전력 수급 기본 계획부터 저도 거기에 들어가서 지금도 작업을 하고 있지만, 이 수소 암모니아 확대를 통하여 발전 부분, 특히 석탄 부분에 대한 암모니아 혼소, 그리고 LNG 발전에 대한 수소 혼소를 적극적으로 국가가 보조금을 통하여 진행하려고 합니다. 올해 처음으로 청정수소 입찰 시장이 열립니다. 청정수소 발전 입찰 시장이 열리면 거기에 일종의 상당히 많은 자금을 투여하여 혼소하는 연료 비용을 보전하게 되는 것입니다. 이렇게 하면 한국은 NDC 2030년 NDC를 달성함과 동시에 2050년 넷제로 전력 부문에서 달성해야 되는 넷제로를 완벽하게 달성할 수 있게 됩니다. 그래서 우리가 야심차게 청정수소 입찰 시장을 준비하고 있고, 다른 발전 부분과 동시에 청정한 발전을 하기 위해서 노력을 하고 있다라고 말씀드리겠습니다. 국내 재생에너지 전력의 보급 및 확대는 상당히 어렵습니다. 한국은 동서로 길이가 한 300km 정도밖에 되지 않습니다. 그래서 태양광 발전을 하게 되면 시간대가 한 11시, 10시 정도부터 오후 한 5시 정도까지 나오는데 1년 내내 평균을 잡아보면 한 15에서 20% 정도밖에 되지가 않습니다. 태양광으로 모든 발전을 달성할 수 없다는 뜻입니다. 그러면 여기에 이 부하를 맞추기 위해서 배터리 자원을 달고 그걸 나중에 방전해서 그리드에 물리고 산업체까지, 우리가 지금 이 매뉴팩처러 인더스트리가 한국은 GDP의 30%가 넘는 제조업 최강국입니다. 이 강국인 나라가 전기로 모든 청정 전기를 달성하기 위해서는 다양한 방안이 논의돼야 되고, 그러한 전기를 재생에너지만으로 달성하기엔 생각보다 쉽지가 않습니다. 풍력 사업도 지금 저희가 많이 이제 앞으로 진행을 하려고 하고, 2038년까지 태양광과 풍력을 합쳐서 115기가와트를 설치할 계획입니다. 그럼에도 불구하고 전반적인 전력화 부문을 탈탄소화하기는 쉽지가 않습니다. 그래서 지금 재생에너지 사용도가 낮기 때문에 아리백 기업들에게는 상당히 많은 허들이 될 거라고 생각하고 있습니다. 그래서 앞으로 이 여러 가지 지리적 여건에 국한된 부분을 해결하고 그리드, 개통망을 연결하는 것이 얼마나 어려운 일이 잘 아실지 모르겠지만 정말 힘듭니다. 그래서 그런 부분이 결국 산업의 전기화를 촉진시켜야 한 여러 가지 방법을 고안하고 있는 중이라고 말씀드리겠습니다. 그래서 지금 우리나라 기업들이 30%대나 제조업, 근데 이 제조업은 거의 대부분이 수출 기업입니다. 반도체, 자동차, 석유화학, 철강, 뭐 비철금속에 이르기까지 전 세계에서 막대하게 경쟁력이 있는 기업들인데, 이 기업들이 탈탄소를 어떻게 할 것이냐가 한국 경제의 앞으로의 핵심입니다. 그런데 재생에너지 환경은 그렇게 좋지는 못합니다. 그래서 저희가 수소 또는 암모니아라는 상황을 암모니아를 활용해야 되겠다라는 생각을 가지고 있고 올해 CHPS 입찰 시장을 열게 되는 것입니다. 수소의 밸류체인은 다 아시다시피 생산, 저장, 운송, 활용단까지 다양하게 있고 사실 이 모든 부분에 한국 기업들이 다 들어가 있습니다. 뭐 재생에너지와 관련된 수전해, 그리고 뭐 CCUS 다 들어가 있고요. 그린 암모니아, 그린 수소, 뭐 또 블루 암모니아, 블루 수소 생산에 전반적으로 다 투여되고 있습니다. 그리고 저장 운송과 관련된 여러 가지 기술을 개발하고 있고 우리나라 벌써 액화 기지가 인천에 이미 들어서 있습니다. 수소 액화 기지가. 그리고 활용단에 있어서는 현대자동차를 비롯한 수소차 시장, 그리고 발전 부문, 그리고 산업 부문의 수소 환원 제철, 철강에서 이제 코크스를 쓰지 않고 H2를 사용하여 환원하는 여러 가지 수소 환원 제철 등등을 계획하고 있어서 한국 기업이 이 모든 밸류 체인에 다 모든 기술 경쟁력을 가지고 있습니다. 그래서 특히 발전 부분도 여러 가지 수소를 활용하지만 산업 부분에서 수소가 굉장히 중요합니다. 저희가 아까도 말씀드렸던 열 에너지 50%, 수송 에너지 30%를 어떻게 전기화로 넘어갈 것이냐, 그게 결국 무언가를 태워서 발전을 해야 되는데 거기에 들어갈 연료가 결국 수소가 될 것입니다. 이 수소는 철강에도 들어가고 아연 공정이나 비철 금속 공정에도 들어가서 환원 작용을 일으킬 뿐만 아니라 연료로서 발전소에 들어가서 혼소를 통하여 CO2를 줄이는 역할을 동시에 함으로써 산업의 탈탄소에 기여를 하게 됩니다. 수소 환원 제철이라는 게 철강업에서 이제 나오고 있는 기술인데, 우리가 지금까지는 철강이 원석이 Fe2O3입니다. 그러면 C를 넣으면 O2를 땡겨서 CO2가 나오면서 자연적으로 발화가 되고 열이 1600도까지 올라가면서 철을 녹일 수 있습니다. 그러나 지금부터는 C를 쓸 수 없습니다. 그러면 H2를 집어넣습니다. 그러면 O2를 땡겨서 물이 됩니다. 이때는 발열 반응이 일어나지 않습니다. 그러면 무언가로 열을 1600도까지 올려야만 철광석을 녹일 수 있고, 또는 이미 환원이 한 번 된 스크랩, 고철을 가지고 철을 생산하려면 한 1000도에서 1200도까지 올릴 수 있는 전기 에너지가 필요하게 됩니다. 이때 전기로의 전기를 무엇으로 공급할 것이냐라는 것이 앞으로의 경제성을 담보하는 일이 될 겁니다. 우리나라 포스코 같은 경우에는 만약에 지금 있는 고로를 전부 전기로로 바꾸게 되면 약 150 트릴리언 달러, 그러니까 한 100 트릴리언 달러 정도를 전기 요금으로만 지급해야 되고 수소의 가격은 따로 산정해야 됩니다. 그 정도로 고가의 에너지를 써야 되기 때문에 징검다리가 필요하게 됩니다. 그래서 저희가 이제 LNG 발전소가 지금 한국에는 약 한 30%의 발전 비중을 담당하고 있습니다. 석탄이 한 30% 되고 LNG가 한 25%, 30%를 왔다 갔다 하는데요. 이 발전소들을 탈탄소화하는 과정이 필요하게 됩니다. 그래서 결국 석탄은 암모니아와 혼소를 통해서 CO2를 절감하고, LNG 발전소들은 수소 혼소, 앞으로는 수소 전소 발전소로 진행하게 됩니다. 그렇게 되면 결국 이 터빈들이 혼소를 했을 때 받아줄 수 있어야 됩니다. 그런데 LNG 발전소는 기존의 터빈을 사용하면서 노즐과 연소기 교체만으로 수소로 전환할 수 있습니다. 수소를 혼소하거나 전소할 수 있는 발전소로 진행이 가능하다는 뜻입니다. 그래서 징검다리 형태로 지금 있는 LNG 발전소를 유지하면서 그 LNG 발전소에 수소를 혼소하는 과정을 통하여 저희가 올해 말부터 시작되는 CHPS에서 이 수소 연료에 대한 보조금을 지급하고, 석탄 발전소는 암모니아 혼소에 대한 보조금, 차액 보조를 지급하도록 되어 있습니다. 그리고 우리나라의 두산 에너빌리티와 하나 임팩트, 하나 에너지 등이 수소 터빈, 수소 연소기 교체, 수소 노즐 교체 기술을 개발하고 소형 한 50메가에서는 이미 100% 전소를 완성했습니다. 근데 수소 가격이 굉장히 비쌉니다. 우리나라 앞에서 말씀드린 대로 결국 그린 에너지, 그린 수소를 달성하기에는 재생에너지 환경이 그다지 좋지 않기 때문에 현재 그런 기술을 개발해서 향후에 수소 가격의 인하를 바탕으로 LNG 발전과 수소 혼소가 동시에 진행되게 될 것입니다. 수소 발전소와 관련된 것들은 현재 GE, 미쓰비시, 지멘스 등이 적극적으로 기술 개발을 동시에 하고 있기 때문에 이런 기술들과 경쟁을 통하여 향후에 경쟁력 있는 수소가 등장하고 터빈 가격이 싸지면 동시에 진행 가능할 거라고 생각합니다. 이 수소 혼소를 통하면 약 70% 정도의 혼소를 통했을 때 CO2를 50% 정도 감축시킬 수 있습니다. 현재 한국의 K텍사노미 상으로는 CO2를 250g까지 낮춰야 되기 때문에 수소 혼소, 암모니아 혼소가 필수적으로 필요합니다. 우리가 2030년 이후로는 어떻게든 화석 연료 발전은 단독 발전은 없을 것이고 연료 혼소 발전이 꼭 이루어져야 됩니다. 일본이나 미국이나 모든 나라들도 지금 수소와 관련된 프로젝트를 진행 중이고, 미국에서는 만약에 지금 선거가 어떻게 될지 모르겠지만 결국 30년도까지 원샷 1kg의 수소를 1달러에 달성하겠다라는 이야기를 원 데케이드 안에 달성하겠다라는 이야기를 하고 있습니다. 그래서 근데 이게 기술적 문제점들이 무엇이냐면 수소는 발화 연소 길이가 굉장히 짧습니다. 이 워낙 원소가 발화되는 그 타이밍이 짧기 때문에 백슬래시 그 노즐 뒤로 숨어버립니다. 불꽃 길이가 너무 짧아서. 그래서 지금 이걸 앞으로 내뿜는 기술들, 그리고 연소기에서 이걸 받아줄 수 있는 기술들을 개발하고 있고, 소형에서는 이미 100%를 성공하고 있습니다. 실험실 단위에서는. 그래서 앞으로 우리 LNG 복합 발전이 한국에 약 161기 33기가와트 정도가 있는데, 이 모든 발전소들이 결국은 LNG를 현재는 사용하지만 향후에는 수소 발전으로 진행할 수 있는 기술 개발을 적극적으로 하고 있는 중이고, 2027년도에부터는 수소 혼소가 현실화됩니다. 한국에서는 암모니아 석탄도 현실화되고요. 그래서 이런 부분들이 전 세계에서 가장 앞서 나가고 있는 국가라는 것을 말씀드리고 싶습니다. 그리고 이렇게 해서 이제 처음에 LNG로 시작할 수밖에 없는 상황들은 결국 그리드에서 있는 전기가 석탄이 좀 있다 보니까 한국이 아직 배출 계수가 높습니다. 그래서 LNG만으로 단독으로 운전하거나 수소 혼소를 했을 때 배출 계수를 적극적으로 낮출 수 있기 때문에 우리나라 환경에 맞는, 대한민국의 환경에 맞는 방법이 일단은 이런 식으로 진행될 거라고 생각하고 있습니다. 자, 그래서 현재 한국에서는 국책과제, 나라가 서포트를 하여 여러 가지 R&D 과제를 함과 동시에 기업들이 자체적으로 LNG와 수소를 혼소하는 기술 개발을 하고 있으며, 현재 두산과 하나 두 개 기업은 미국에 있는 기업들과도 협력해 가면서 이 기술을 개발하고 있습니다. 현재 GE는 50% 혼소가 가능한 연소기 개발을 오하이오 주에서 2030년까지 하겠다고 지금 실증 사업을 하고 있는 중이고요. 지멘스는 30% 혼소를 지금 개발 중이고요. 미쓰비시 같은 경우에도 현재 30%를 타깃팅해서 준비 중입니다. 두산 에너빌리티는 이미 S1과 S2 타입을 대상으로 수소 혼소 50%를 실증하고 있고요. 현재 380메가짜리 열병합 발전소에서도 실증을 할 계획입니다. 하나 임팩트도 네덜란드와 미국을 중심해서 혼소 35%까지, 그리고 현재 소규모 스케일 5메가 정도 단위에서는 이미 100% 수소 혼소를 성공시키고 있는 중입니다. 그렇기 때문에 현재 LNG 발전소가 있는 우리나라 입장에서는 현재 사용할 수 있는 LNG 발전소를 통하여 열을 공급하고, 그러니까 전기를 통하여 열 전환을 이룩하고, 향후에는 수소를 통하여, 특히 암모니아 수소를 통하여 친환경 발전업으로 산업의 탈탄소화를 위해서 진행할 계획임을 알려드립니다. 한국은 굉장히 열심히 노력하고 있고 글로벌 사회에 책임 있는 나라로서 역할을 담당하게 될 거라고 저는 자부합니다. 감사합니다.
네, 고맙습니다. 단국대학교 조홍종 교수님의 강연 함께 하셨는데요. 탄소 중립과 또 에너지 안보 확립, 또 신산업 육성 등 수소 경제의 중요성과 함께 산업의 탈탄소 전기화 방안에 대한 귀한 의견 나눠주셨습니다. 고맙습니다. 자, 이어서는 Japan Korea Low Carbon Ammonia Benchmark and Introduction이라는 주제로 알구스 미디어의 SVP Energy Transition이십니다. 팀 하드님께서 발표에 수고해 주시겠습니다. 여러분 힘찬 박수로 맞아주시기 바랍니다.
Thank you very much. Well, good morning. If the professor had to apologize for slides and language in Korean, then I must apologize for doing the same in return in English. My name is Tim. I'm from Argus. This is the topic I'll be speaking about today. It may seem a slightly unusual topic, but given that Korea is at the bleeding edge of ammonia usage, low carbon ammonia, low carbon hydrogen, hopefully this will help explain why I think it's important to look at benchmarks from the point of view of security of supply and the stability of Korean electricity pricing. So broadly speaking, commodities tend to move across these three stages. At the beginning, the offtake stage, it's a novel commodity, such as LNG many years ago. There's a lot of risk in these areas, both for the supplier and for the consumer. And so what you find is that suppliers and buyers come together to share risks to ensure that they can bring production online. And offtakes have to be put in place so that new facilities can be built. Those tend to last for about 10 to 15 years, those offtakes. The second stage follows on from that as those offtakes roll off. It becomes a benchmark stage where the prices are negotiated on an annual basis normally, as are the volumes. And the final stage is the spot stage. It's the one I've been spent most of my life working in, actually, and it's what's brought me to Korea for many years now, between 2008 and 2020. If you were buying iron ore or coking coal or scrap, you'd have been buying it using a number that I was helping to produce. At the moment, however, low-carbon ammonia, low-carbon hydrogen, very much on that far side, that beginning stage. That poses a problem. And the problem is, how do people negotiate what the price is going to be? They have to negotiate a price. If they don't, there will be no offtake signed, no binding offtake. And without a binding offtake, there will be no final investment decisions. No final investment decisions means no low-carbon hydrogen or ammonia coming. The other thorny issue is that offtakes, or the prices agreed, have to be dynamic. They can't be fixed because these are lasting for very long times, over a decade. If we look at the hydrogen offtake structure, these are all the variables that have to be negotiated between buyers and sellers. Rather a lot, no matter whether it's grid-connected electrolyzers or renewable-coupled electrolyzers, whether it's fossil fuels for CCS. There's a lot to discuss there. And in fact, the number of principles globally talking about low-carbon offtakes probably equal to about the number of people in this room. Now, if we all went away and had discussions involving each of these variables and then came back to compare notes, we'd end up with very, very different looking offtake agreements. They would all be very varied. Now, on day one, month two, that doesn't really matter. But those little differences over time will accumulate. And so those differences will widen over time. And that's a problem. It's a problem for people wanting to keep an offtake running, because when one party feels that they're out of pocket, then you're coming straight away to having to renegotiate your contracts. That defeats the point of a 10 to 15-year offtake. It gets worse, of course, when you look at derivative products. Ammonia is quite often looked at as the vector to move low-carbon hydrogen products from overseas over blue water. And of course, it's expensive in Japan or Korea to domestically produce these items. So that basically means that there's more points that have to be discussed. A synthesis loop stage to combine the hydrogen and nitrogen to make ammonia. It has to be shipped from the US, from the Middle East, etc., to either Japan or Korea. And there's possibly subsidies involved as well. These all have to be discussed. Now, the alternative to that, of course, all of those different variables, is to look at using an index. Before talking any more about that topic, I will make the point that this isn't the first market that's had to wrestle with these issues. LNG is one that's discussed a lot at the moment. And it started up probably around 1969, 1970, and it faced very similar problems in terms of how do we price our product. Very much hydrogen and ammonia sit in that box on the far left where LNG used to be. And the problem for the LNG buyers and producers was they wanted to use LNG pricing, but there was no pricing. There was no product yet. And so people used proxies instead. They used gas proxies, and they used oil proxies. Now, they went away and had opaque bilateral discussions, and then they came back, as I discussed earlier, and compared notes, and everyone had decided to use something else. Some used TTF, some used Henry Hub. On the oil side, still Brent is being used, and of course LNG itself, now that there's a spot market, is also being referenced. So in the current market today, there's at least 4 references for LNG. As I say, TTF, Henry Hub, Brent, or spot LNG. That's not an ideal market structure. As the low-carbon industries get underway, I think that there's a better path forward, and that is to be very specific about the product that you're buying or selling, and actually reference that directly. So it's much easier to use a low-carbon ammonia number if you're going to buy low-carbon ammonia than a proxy, for example, Henry Hub or TTF. And that will actually help the market to evolve as it goes through these market gates that I discussed earlier, from the offtake stage to the benchmark stage to the spot stage. I would say, very broadly, it's very helpful for the market, even at this stage, to have a reference for what the cost of low-carbon ammonia is likely to be. Because there are many numbers that have been out there, but they've been printed over many, many years. And so the issue is that some of the numbers that people are thinking about and negotiating around may be pre the interest rate rise, maybe pre-Ukraine. And so you've got quite a wide divergence between where buyers and sellers think that pricing should be. And I think that a widely published number is useful to get away from some of those questions. I'll give you an example using cake. It's a ridiculous example, but I'll use it anyway. As a product, there are companies out there looking to buy 500,000 tons a year of low-carbon ammonia. So if we said the same for cake, 500,000 tons a year of cake, it's a fairly simple ingredient list for a lemon cake. There's not much to it. And in fact, there's less on that little ingredients list there than there was on that list of variables I showed earlier for hydrogen's conversion to ammonia. Not too many. But if people said, I will only have one factor which I'll use to escalate the price of that cake or de-escalate it, I'll use wheat, for example, that's kind of not ideal. It's not just wheat. I mean, wheat isn't even flour, so that wasn't even on the ingredients list. And I actually see that as a very, not a bad analog, actually, for how some people are looking at using, say, a gas price just to price ammonia. There are other alternatives as well, but I'll make the point that if anyone has ever tried to hedge natural gas as a proxy for LNG, it's an uncomfortable trade, a very uncomfortable one. It's always best to avoid basis risk, and basis risk often happens when you use a proxy rather than directly talking about the commodity that you're trying to buy or sell. So we created the Japan-Korea low-carbon ammonia benchmark, or JK Lab, specifically to meet that need. What it is a US-based autothermal reformation plant using carbon capture and storage to produce over 1 million tons a year of low-carbon ammonia. It's a mass-balanced and process-engineered model, which a number of our teams, both from the consulting side and from my editorial side, have put together. It uses Henry Hub as an input, but it also uses local power costs. It includes the costs for carbon being not just transported, but injected into the ground and monitored in the long term. And the end product, of course, is low carbon or blue ammonia. That, at that point, is ready for shipping to either Japan or South Korea. The JK Lab is not just obviously the cost of low carbon blue ammonia, it's an all-in cost, it's a CFR cost delivered into Japan or Korea. We use medium gas carrier vessel rates to transport from the US Gulf to Northeast Asia, actually to CFR Ulsan. And those are produced by our freight teams. We use the medium gas carrier vessels mainly because whilst very large ammonia carriers are being planned, they're not in service yet. And even if they were in service, the port infrastructure isn't available today to be able to discharge and store a very large ammonia carrier vessel's hold. Once they do come into service, we expect that to reduce freight costs substantially. At the moment, they're about $150 a ton, so that's not small. But for now, we're using the medium gas carrier vessels, which are different to other types of vessels, obviously. As I said, 10 to 15 years is a very long time. And so because of that, because of the uncertainties involved in such a duration, you can be very sure that you'll have many disruptions on different routes during that time. The two basic routes are via the Panama Canal or via the Cape of Good Hope. The freight rate we always use is the lower of those two. So that's just a normal, economic, rational selection. We published CFR Nihama, Japan, as a differential as well, because it is the Japan-Korea benchmark. And that's what it looks like. We publish including and excluding some of the US incentives via the IRA scheme. This is excluding the 45Q incentive, which is about $85 a ton for injecting carbon into the ground. When we look at it, we see a rebate of around $120 a ton for carbon because there's more than a ton produced, essentially. So it's not cheap. It's not a cheap commodity. When you compare that to something like coal, that's $150 a ton. So as we're over 650 here, and this is the cheaper version, this is blue ammonia, not green, it's not cheap. I don't think it's only just useful for, well, coal-fired coal generation is where it's initially being considered. But of course, the second industry to start looking at using ammonia is the maritime industry. It's also a useful number for them. But equally, I think it's actually more than a regional benchmark because other regions could use this too. The US is by far in the lead for the number of facilities that it's trying to bring online for ammonia production. But other areas, that means, will have to compete against them as a benchmark. And so they'd be just as likely and able to use this as a reference. It's also rather useful to have a number, a single number, not just for the market to use, not just to insert into offtakes, but also so that you can actually compare what the relative cost is to other things. So having a number like JK Lab allows us to compare what the premium is to something like the counterfactual alternative fuel that's being substituted. So these are the differentials to 6,000 kcal coal from Newcastle. The blue line at the bottom is including 45Q. I think I've mislabeled these unhelpfully. and the expensive line at the top is excluding it. I do think that it's a 10-year period that you get to use 45Q subsidies for. So I would very much want to be negotiating to have that included in my offtake if I could. It also allows people to be able to see what the actual cost is in terms of an 80-20 co-firing ratio. So an 80-20 co-firing ratio is actually on an energy balance, not on a weight balance. So it's not 800 kilograms of coal and 200 kilograms of ammonia that we're talking about. It's 800 kilograms of coal and about 270 kilograms of ammonia. So you can combine those to see what the additional cost is for a 20% decarbonisation, which isn't insubstantial. But these are the sorts of things you can do when you have a single number, because the alternative is everyone looking at spreadsheets and trying to work out what the cost is that's being paid. We published this in our Argus Hydrogen and Future Fuels publication. I'll make note at the bottom there. I said there was a big differential between the excluding 45Q and the including. It's about $120 a ton, just to quantify what that gap is, which is why I'd like to negotiate for that if I was a buyer. And we also make it quite widely available as well on social media, especially on professional ones like LinkedIn. But we're also going to try and make it available as well to anyone that wants to see this number via straight email. So if anyone has an interest in it, please let me know, and I'll add you to the distribution list for that. So trying to make it as widely as available as possible, not just to people in Korea, but also in Japan, in the US, and elsewhere. Thank you very much.
맞습니다. 일본과 한국의 저탄소 암모니아 벤치마크에 대해서 발표를 통해 소개해 주셨습니다. 자, 이어서는 세 번째 연사를 소개해 올리겠습니다. 에머슨 오토메이션 솔루션의 디렉터 서스테이너빌리티 앤 디카보나이제이션 아시아 퍼시픽이십니다. 마틴 반 데어 멀베님께서 Future Proofing Hydrogen Project with Boundless Automation이란 주제로 발표 준비해 주셨습니다. 그럼 힘찬 박수와 함께 발표 청해 듣겠습니다. 큰 박수 부탁드립니다.
Good morning. Again, apologies, another English presentation. So my name is Martin van der Merwe. I am the Sustainability and Decarbonization Director in Asia for Emerson. And today I'll talk a little bit about how Emerson's technology is impacting hydrogen projects and benefiting hydrogen projects, and share some examples and some proven results as well. Just briefly, a little bit about Emerson. We are a global automation and software company. We participate in all industries, from energy to medical and manufacturing industries as well. We've been in Korea for over 35 years, supporting industry here. And we are continuously evolving and developing technologies that help industries like hydrogen become more viable with technology that we provide in the automation and software space. Recently, we acquired controlling stake in AspenTech, and that enabled us to combine our software applications and technologies, and I'll talk a little bit about what we're doing there in more detail. So how is Emerson's technology applicable to hydrogen? Well, our technology assists the whole value chain from renewable energy all the way through to end-use applications. We do that with our instrumentation and control technologies. We have actually very proud to have won the preliminary award for one of our safety valves for liquid hydrogen. Liquid hydrogen is an area where we are developing quite a lot of equipment. We also have a liquid flow meter, liquid hydrogen flow meter that we've developed to assist the refueling industry and the transportation industry. All of this information coming from the instrumentation layer is fed into our control and safety system layer. And this is where a lot of the complex control, advanced control is implemented. And then these layers feed information up into the enterprise layer so that additional optimization, analytics can be performed. So you can see, because of the complexity of the hydrogen value chain, it is critical to have these applications, instrumentation and control layer all very well integrated, not only to improve the outcome of the project, but also to reduce the cost. So we call this concept boundless automation. And we continue, as I mentioned, to develop technology that simplifies the installation and operation of the instrumentation, including diagnostic information, built-in applications in the actual equipment themselves, so that you can optimize continuously the operations that you have. We're also simplifying how the control layer operates. So we virtualize and use containers, containerizing all of the applications to enable secure and safe operations of the control layer. This reduces a lot of infrastructure costs, a lot of servers and equipment that you would typically install in a control and equipment room, and ultimately enables the capability to move data up into a cloud environment. And the main objective, of course, is to have contextualized data from the field into the enterprise layer so that you can have people that are responsible for safety, people that are responsible for operations, people that are responsible for maintenance, have the data that they need at their fingertips. Now, in a typical automation project, and a typical hydrogen project, actually, automation scope is only 2 to 3% of the CapEx investment. That means that a lot of the times the decision is delayed to very late in the project, typically feed or even after feed. However, it's a missed opportunity because the technology that is being developed and that are available today significantly impacts how you would construct and engineer a project. If you don't take advantage of this architecture very early on in your feasibility and pre-feasibility, you miss the opportunity to reduce that construction and engineering cost. So it's very important to consider automation very early in a hydrogen project. I thought I'll give an example just to clarify how this eventuates. This is the flow that an actual customer, the journey that an actual customer took to make benefit of the technology. So right in the top left corner, the customer used AspenTech Fidelis software, which is a Monte Carlo simulation software that allows you to simulate at a very high level all the different components in your hydrogen value chain. This includes taking the renewable profile that you will expect, feeding that into your different electrolyzers, and even evaluating different electrolyzer technologies based on their operation, their efficiency, their output, and then building out that into storage and end-use applications, including battery storage, for example, with fuel cells. So they did that, and you can run these simulations over many years using all this data input that you have. In this case, they ran a 5-year simulation to be able to justify the investment that they have and to be able to attract investors as well. So they were able to prove that they are economically viable. And from there, they went and then developed further modeling to implement the actual project. So they obtained HYSYS models from the electrolyzer vendors, and they've used that, integrated that into their process model, ultimately into a dynamic process model, which is right here at the top right-hand corner. That effectively means that they developed a process digital twin. So the concept of a digital twin, last night I played screen golf for the first time, and I was sort of saying that this is a lot like a golfing digital twin. So a process digital twin is simulating the actual electrochemistry process. At the same time, in the automation layer, we can develop a automation digital twin. So this is where the actual configuration of the control system is done, and we can link the process, the virtual process, to the virtual control system. And this is the same configuration that you would implement in the real world. So you can test, you can develop the graphics, you can test the configuration all in one go. You can also go as far as to develop a virtual environment that simulates the actual constructed facility. So this gives you an example of how they leverage some of the automation technology using wireless instrumentation and electronic marshalling technology that reduced the construction cost, and they reduced the engineering effort by doing a lot of this work in the front end of the project. Of course, this depends a lot on the project size, and we focus a lot on fit for purpose in the hydrogen space because there's no point in spending too much money when it's not going to deliver value. So we see as the hydrogen projects are now evolving, and as Tim presented, the evolution of the industry is moving forward, we see these projects also increasing in size. So from the small scale demonstration projects now evolving into larger scale projects, and that's one of the examples I'll share today. As you move up this chain, the technology becomes more critical, and the capability to impact and reduce cost and improve efficiency becomes more critical when you evaluate the technology that you're going to implement. So these are just a few references of hydrogen production projects that we are involved with, and you will see many of them include MAC, Main Automation Contractor Scope. So this is where we provide instrumentation control layers, as well as the AspenTech software solutions. And you'll also see many of them have used the modeling, upfront modeling that I described just before, to implement their project very early on and optimize their project very early on. We do, however, also participate in a lot of the innovative projects. So even though there are some small-scale projects, there's a lot of innovation happening in this space. One example is the Poseidon project in the Netherlands, where they're using decommissioned offshore platforms and converting them into hydrogen production facilities that can inject hydrogen into the gas line that's already available. And that way they can actually make those depleted assets valuable again. And they have all the infrastructure already built. So there's a lot of innovation happening in this space as a lot of the LNG transition moves into hydrogen. So many of these projects are involved in that, and we participate and support the development, also in new electrolyzer technologies like anion exchange membranes and solid state electrolyzers as well. Now, jumping into the one of the examples mentioned earlier, and Chevron and Mitsubishi ACES Delta project in Utah. Obviously, Chevron is a major sponsor of the event as well, which I didn't know before, so that was just a coincidence. This is a very interesting project. As Professor Hong Chong Cho shared, the ability to use hydrogen and inject hydrogen into a combined cycle power plant is an opportunity for de-energizing, or decarbonizing, I should say, the grid. This is exactly a project that's doing that. So the intent of this project is to use the additional renewable energy that's available during the day in the US grid, the excess renewables, and then making hydrogen and then storing that in salt caverns that they can then deploy through a Mitsubishi turbine in a combined cycle power plant and inject that back into the grid during high demand. We provided the control system, the energy control system, and I'll share a little bit about the learnings we had on this project, given the size of the project. So the complexity, as I mentioned, when you start scaling up a project, becomes quite high. This project has 40 5.5 megawatt Hydrogen Pro electrolyzers. And traditionally, in the smaller projects, the electrolyzers will come in a skid package with a balance of stack, all sort of integrated. And when you have 40 of those type of skids deployed, there's a lot of inefficiencies built in. There's a lot of duplication in the process, in the balance of stack that you can eliminate. And also there's a benefit to eliminate that because you have up to 3 times more instrumentation and control to manage and maintain if you don't optimize that over the life cycle of the facility. The other complexity when you start considering how you are going to operate all of these electrolyzers is quite a challenge, the control aspect of it. Using the Fidelis tool that I mentioned earlier, the project went and evaluated different options, different combinations of these electrolyzers, and they settled on using 2 electrolyzers together as one train, so a train of 11 megawatts, and then having then 20 of these trains connected together and having the balance of plant integrate all of those. Now, the operation of an electrolyzer, there's an example of a state diagram there of a single electrolyzer operation. Typically, that is done in a small PLC, and when you start to then have this master control, which is the 2 functions you see up there, it is very hard to ensure connectivity. And if you make any changes in the electrolyzer itself, then it is quite a process to go and do that on 40 or 20 different PLCs. So in this project, they decided to integrate the actual electrolyzer control into the Emerson system, as well as using the master control or the high-level production master. We also had to implement the energy management system. So these 2 functions work together. Because they are taking excess renewables, means that this plant has a lot of variability in it. So the energy management system would determine how much additional available renewables exist, and then set the set point to the production master that defines which electrolyzers will be operated based on its different states. So you can imagine there's just a few variables that I listed there in the consideration of those functions that we developed into this control system. So it's quite an interesting project for us. It's quite a large project globally, and there's a lot of learning that have come from this project. And it is in construction and will be operational in 2025. So in summary, one of the key things that we have experienced to accelerate hydrogen projects and de-risk hydrogen projects, it's critical to consider what technology can be used and what technology can do to make this project viable very early on in the design phase. With that, it means that you can accelerate the project, you can reduce the cost. Up to 30% of the construction cost can be reduced by using smart field instruments and smart control systems. And ultimately, that will reduce the scope of the project, reduce the amount of equipment being installed, and ultimately reduce the operational cost for the project. As I said, it's critical to ensure that you can integrate as much of these systems as possible. So having a automation partner that can deliver the full scope from instrumentation all the way into the analytics applications in the enterprise layer is of huge value. So if you wanted to know more about all of these technologies, we have a stand with all of this technology displayed down in the exhibition hall. So feel free to come and say hello and ask more questions about what we do in hydrogen. Thank you very much.
네, 마틴 반데어 멀벤님의 강연 함께하셨습니다. 이 미래 수소 프로젝트에 대비하기 위한 효율성과 또 지속 가능성을 극대화할 수 있는 자동화 기술 도입 방안에 대해서 귀한 의견 나눠주셨습니다. 고맙습니다. 자, 이어지는 강연은 Green Revolution, Navigating the Decarbonization Frontier라는 주제로 포테스큐 제너럴 매니저 세일즈 앤 마케팅의 린다 레이님께서 수고해 주시겠습니다. 여러분 뜨거운 박수로 맞아주시기 바랍니다.
Good morning, everyone. It's truly a pleasure to be able to stand here and then introduce Fortescue's efforts in navigating the decarbonization and energy transition kind of frontier. My name is Linda Lay, and I'm the general manager of Fortescue Energy Asia. With leadership, with leadership experience, spending at major international companies like Vitol and Cargill, I have been at the front line of the global energy transition, aligning my career with the shift towards sustainable energy solution. I joined Fortescue about 1 year ago, and I have the privilege of contributing to the company's mission to decarbonize and become a global leader in green energy and technology. So I will pause here to give the translator some seconds to translate this into Korean. This is the newly refreshed Fortescue vision. And I would like to highlight a few words on this slide. The first two are technology and energy. You probably know Fortescue with our prior name as FMG. We are the fourth largest iron ore producer in the world, and we are very proud to be the lowest cost producer of iron ore in the world as well. And with very strong balance sheet of roughly about $5 to $6 billion as net profit and about $5 billion cash on hand, that we decided to transform ourselves from a pure metal producer to become a decarbonization technology as well as go into the green energy sector as well. And how we are going to do that? We are committed ourselves to be actually develop this technology as well as the green energy projects very rapidly, profitably, and globally. And speaking of rapidly, I want to let you know that actually we just established our company about 20 years ago. And here we become so fast growing to become the fourth largest one. The reason is because we've always been driven to not only achieve the goals, but also to achieve them very, very fast by using and creating cutting-edge, innovative technology to do things that no one think that we can do in a very short period of time. And also about the profitable here, we do not believe that decarbonization is only a big-ticket cost item. We believe that it actually can generate huge revenue stream for any company who committed to do that. Reason being that when we deviate ourselves from fossil fuel, which is highly associated because of geopolitics. So you actually count on Mother Nature, like for instance, sunshine, water, and wind power, that to power your operations, that you have the ability to actually generate very, very strong revenue stream for the future. So here is a slide to showcase that what Fortescue actually, Dr. Andrew Forrest and every employee of Fortescue pledged to the world. Before I share with you the targets that we try to achieve, let me share with you a few statistics. Every year, Fortescue, as the fourth largest iron ore producer in the world, use roughly about 1 billion liter of diesel oil. And we are emitting 2.5 million tons of carbon dioxide into the atmosphere. And how we are going to address that? Although this 2.5 million carbon emission is relatively small compared to our peers or buddies from the steel-making company that generally emit 80 million to 200 million kind of carbon emission, but we still feel shameful to actually emit that 2.5 million into the atmosphere. So what we are going to do is that we are going to reduce this 2.5 million in scope 1 and scope 2 by 2030 to achieve real zero. What does real zero means? It has two significant meanings here. Number one means that no fossil fuel by 2030 of Fortescue's operation. Zero single drop of diesel oil in the future. The second meaning of real zero is that we do not believe in carbon offset across our operations. We do not believe in that because we think that you still can use fossil fuel and buy carbon credit to offset it. That is not the real decarbonization, according to our dictionary. So our scope 3 emissions reach 260 million tons of carbon dioxide equivalent annually. And 98% of that is actually coming from the steel-making process. We know that we are part of that sector that create enormous emission globally, and that's why that we decided to actually to decarbonize, not only for ourselves, but also support our partners in scope 3 to do the same thing as well. And obviously, it's very, very challenging, and it's one that we know we are up to. So to achieve our targets, we are going to use a combination of known and proved technology, and we're also developing some innovative technology as well. Let me give you one example that how battery is going to change our operation in our mine site. The one that you see here is called Roadrunner. It weighs 240 tons. And then at the front of the truck, there's a battery that is 15 tons heavy, okay? And then this is going to be a zero emission truck that we're going to put into our plant, into our site, okay? And it's going to emit zero carbon dioxide into the atmosphere. And from a low charge mode to a fully charged mode that it only uses 30 minutes to get there. By 2026, that we are going to use hundreds of these similar kind of trucks in 5 of our sites in Pilbara area. And the battery, we use the technology from WAE, William Advanced Engineering. The equipment is produced by Liberal Hill, and then we assemble in Perth, and we send it over to Pilbara. So speaking of a global team, globally to accomplish our vision, that is a very, very good example that I want to showcase here. And maybe you also noted that just yesterday that Fortescue made an announcement that we're going to have a $2.8 billion of what we call the green equipment partnership with Liber Hill Mining. So by 2026, that we are going to use 475 kinds of zero carbon emission equipments on our sites. Okay. We believe that battery, green hydrogen, and green ammonia will need to be all used as a combination solution to solve the decarbonization challenge. We cannot rely on only one or two, but we need to use a portfolio of technology and solution that will tailor-made to each different situation. And this beautiful vessel is called Green Pioneer. And it is actually the first use ammonia as bunkering fuel in a dual-fuel ammonia power vessel. Because Fortescue sent roughly about 200 million metric tons of iron ore from Pilbara to our customers all over the world. And each year, that shipment creates 3 million of carbon dioxide, with roughly about 10% of that is coming from our own vessel. We're also thinking that how we are going to address that issue as well. It's not only an issue facing Fortescue, it's actually facing the whole shipping industry. So therefore, we invest heavily to produce, design and construct this first use of ammonia as a bunkering fuel of the vessel. The success of Green Pioneer marks a significant milestone in multi-fuel bunkering capability developed to support the digitalization, decarbonization, and manpower development for the international shipping. The IMO have sent multiple teams on board to understand how ammonia as a marine bunker can be safely transferred as well as being operated on a vessel. And these provide valuable experience to help the whole shipping industry to understand how to use that as a marine fuel. So while battery can be critical to use to decarbonize, we also understand that it cannot achieve total decarbonization on its own. So we have to also think innovatively and smartly how to use other energy as a source, like for instance, green hydrogen and green ammonia, we believe is a practical and implementable solution. Therefore, we are now starting to develop green energy and hydrogen projects at scale in regions that have a few attributes. Number one, we need to build a project in region that with very cost competitive electrons. So to generate cheap, cost-efficient green hydrogen and green ammonia. We also plan to build our projects in regions that deviate themselves from geopolitics. For instance, like countries like India and Middle East that is relatively, like Oman, country like Oman, that is very safe. And also the third region, other factor that for us to consider is that we wish to also build projects in countries that strongly advocate green hydrogen and green ammonia. So therefore, our board FID 2 projects, and that makes Fortescue one of the first companies globally to have achieved 2 FID projects. One project is in USA, that is the fast-to-market project, which will produce green hydrogen to service the transport and mobility industry in California and the nearby states. The COD of that project is supposed to be by end of 2026. And the other project is in Australia. It's called Gladstone Pan 50 project. It is a 50 megawatt green hydrogen project that allows us to produce and market the green hydrogen, right? And so by end of 2025, that we supposed to actually produce 8,000 kind of a green hydrogen per annum to supply to many of the hard-to-abate industry nearby, for instance, like sintering plants or steel mills and etc. And my colleagues from Hydrogen Fuel System are coming with me to attend this seminar today. So we have a booth, and we welcome you to say hello and then understand one of the most advanced PAN technology in the world. And in a parallel, we'll also develop other hydrogen electrolyzer technology, like for instance, alkaline as well as AEM. So there are many other projects in the pipeline that we're developing other than the two already FID. So the one that we showcase here is in Horzions, Norway, which is our flagship 300 megawatt green ammonia plant in Norway. And the COD time is supposed to be 2028. And by then, we are going to produce over 230,000 tons of green ammonia that is going to ship to Europe to supply to multiple hard-to-abate kind of sectors, like petchem industry, refinery industry, and then also the steel-making industry as well. And this is a project that highly regarded by the European Union. They have endorsed and also chosen to actually significantly invest in this facility, awarding a grant of 200 million euro as part of the Innovation Fund in 2023. We also have a project in Brazil at the port of Passim. If everything goes well, that we're about to FID this project very soon, and it's going to produce about 1.1 to 1.2 million of green ammonia, and with a main destination in Europe, and also portion of the molecule will actually come to Asia as well. We hope that in the future that chaps in Korea can use some of the green molecule produced from Passim. So how we're going to do to drive forward? And obviously, we believe advocacy. We believe that we need to lobby the government as well as very critical stakeholders to work with us to help the world decarbonize. And Green Pioneer that I just showcased in the previous slide is a perfect example how Fortescue pulls strength from different stakeholders, government agencies, academia, and research institute to achieve our goal. And also, we believe that we should continue to to build and construct good cost-competitive projects in the world to make sure that there will be sustainable green energy to help the world to get there. And the last one is obviously that we wish that we can continue to innovate in the technology, because the cutting edge as well as the innovative technology will revamp the whole value chain, existing conventional value chain, and then create a new one. So that said, that I'm going to pause here, and I believe that it would be great that for me to share a video that our chairman, Dr. Andrew Forrest, recently shared with our global team to give you an idea of who we are now, but more importantly is where we are headed to. Can you please play the video quickly? Yep.
준비해주신 영상 자료까지 함께 시청해 보셨습니다. 글로벌 탈탄소화를 위한 포테스큐가 추진하고 있는 이 주요 에너지 프로젝트들 소개해 주셨고요. 앞서 영상을 통해서 시청하신 것처럼 2030년에 달성하게 된 이 포테스큐의 제로 이미션 여정 저도 함께 응원하도록 하겠습니다. 좋은 발표 고맙습니다. 자, 이제 5번째이자 리더스 서밋의 마지막 강연입니다. 지멘스의 비즈니스 디벨롭먼트 매니저, 하이드로젠 마켓 아시아 패시픽 리전이신 프레데릭 틸란드님과 함께 지멘스의 하이드로젠 비즈니스 리더이십니다. 홍정표님께서 H2 Production Plant from Conceptual Design to Operation이라는 주제로 함께 발표에 수고해 주시겠습니다. 여러분 뜨거운 박수로 환영해 주시기 바랍니다.
So good morning, everyone. So it's a pleasure today to be here and discuss hydrogen with you. So our topic is about, let's say, how we help, let's say, all the different stakeholders in this hydrogen economy to develop, let's say, hydrogen project. So we'd like to share about that today with my colleague JP from Siemens Korea. So, but first, let's say, let's have some few words about Siemens to have maybe some better understanding what we are doing in the hydrogen economy. So personally, I'm part of what we call digital industries. It's basically a division where we are developing lots of technologies, especially in the range of digitalization, but also automation for this industry. We have smart infrastructure. It's basically the division in charge of all the electrical components that we're delivering for hydrogen project. Mobility is also something very important at Siemens. We are also developing hydrogen fuel cell train that are also being implemented and developed in some region in the world. And last but not least, we have Siemens Financial Services. So here we provide support financing to a hydrogen project. We are participating, for example, to H2 Green Steel in Europe currently in terms of equity, but we have different contribution that we can bring to the hydrogen economy here. And then Siemens Advanta. So here is about consulting. So now we are also focusing on this hydrogen market, so we can provide different type of consulting and helping, let's say, project developer and so on in this range. Here I would like also to mention Siemens Energy. So I just explained what we are doing. What we are not doing is making electrolyzers. So this is Siemens Energy. So it's, let's say, it was our big brother before, but now we are, let's say, separated since 2020. We are still collaborating a lot on many projects, but we are somehow two different companies now. So how now we are interacting, let's say, in this hydrogen economy. That was a very good presentation from Fortescue just before. We are collaborating, for example, with these kind of companies, especially in the PEM50 project. And we are trying to participate along the whole project life cycle, typical project. So from the very beginning in the feasibility to, let's say, operation. And we do that along the whole, let's say, hydrogen ecosystem. We'll be involved in, let's say, green hydrogen project, but also green ammonia, if we talk about Power-to-X, transportation, and also the use of hydrogen to decarbonize our industry. Different topic. My colleague JP later on will share some references that we have. So here's the main topic where we are participating. I mentioned financing and consulting. That's definitely a important area. But where we also develop some solution nowadays is about design, simulation, and it's all around digitalization. So it's here about helping, let's say, a project developer to successfully develop their project in, let's say, effective and cost manner. And later on, we have also a lot of equipment that we provide, let's say, in a typical project operation execution. And this is, for example, the automation part. We'll have also some few words about that. but also the electrical part. We provide, for example, all the energy management system, all the low and medium voltage equipment, and so on. So, yeah, today we see some key challenges in that hydrogen industries. One of them is about feasibility, especially how to convert all these announced projects to something real. This is a big challenge, and we see important here to see how we can help the different stakeholders here. Scalability, we see many small projects or let's say demonstration project that needs to go to a much larger scale, or let's say to more to industrialize, to be industrialized. So here again, this is also a need from the industry there. And the last but not least, we need to bring down the cost of hydrogen, and this is all about efficiency, not only capex but also opex and so on. So here also we bring some solution to this industry. At Siemens, so we think that simulation, especially digitalization, are really key in order to solve those issues I just mentioned. And we are trying to bring a lot of innovation in that area. So I will share some solutions that we are implementing. And the idea from Siemens is to develop this digital hydrogen plant. So what is it about? We are covering different sectors. So this is about the design, engineering, automation, and especially simulation of your plants. So in order to address that, we have developed some presentation where discussing a bit about the digital twin, but this is very specific to the hydrogen market. So we are developing this integrated digital twin. This is starting from the left-hand side with the process simulation. So here we have some tool in order to optimize, for example, the electrolysis or the compression of hydrogen. So here we help, let's say, a technology developer or provider to optimize their technologies. We also, at this stage, optimize not the technology itself, but the project, overall project. And it could be a project to produce green hydrogen and convert it to ammonia. So we try to have a more holistic view on the project, and then to provide tools to simulate and optimize the project. I will give you an example after that on that. So when you have done that work on eventually your project, you can use that information in the next step, in the engineering phase. So here we have the next tool that we provide to that market is the COMOS. So it's an engineering and planning tool. So here we integrate all the information that we have been developed and create in this feasibility design phase. So here you can do all the P&ID and so on. So develop, let's say, more the project in the feed and later on execution phase. The last part of this digital twin is the automation. So from the planning engineering tool, we're able to transfer all the data and create the automation concept of your project. So all pre-engineered. So this is our thematic platform here. And the last piece is the CMIT at the bottom. So here about simulation, but here's not the process, but the automation simulation. So here you're going to simulate all your design, how you've been developed, especially in terms of automation or the electrical parts, and see how it works in real. So we can do, for example, virtual commissioning, or let's say use that tool to do training of your staff. So the overall, let's say, digital twin is integrated. That means any change that you may implement in your CMIT, because you realize that some modification are needed, will be implemented in a whole, let's say, digital twin. So I will now give you just a bit of example. It will be a short video that I will explain. So just want to show this is the basis of this, let's say, hydrogen plant. I guess not so special for you, but oops, I haven't pressed anything. Okay, all right. Okay, so this start, yeah. So here I would like to show you how we can use our software GPROMs in order to develop project. Let's say if you want to develop a 180 kilogram per hour hydrogen plant, then you can use GPROM. So we have a library of different processes. This is physics-based blocks. So here you will create your project from the energy part. That could be different scenario. Like in that case, I think it's wind. And then you implement the electrolyzers, different technologies are available, and all the different components of your project. Like, could be compression, purification, and of course the off-taker. This is very important. So you're going to define the main characteristic of your project and what you want to simulate and so on. And then the simulation will start. And the idea is to provide all the key information for your project. That will be the heat and mass balances, the energy consumption, and so on. So you get all the critical data for your project, and then it will start the, let's say, the simulation parts. You can eventually change your scenario for the energy. You can integrate your PPA. You can integrate the grid and together with renewable and do different simulation. Another tool that we have developed also here is this LCOH calculation. So it will integrate as well all the different OPEX and CAPEX of your project and will provide, let's say, the calculation of your, let's say, hydrogen cost. Yeah, so in that case, it's about €6, something maybe we'd like to achieve. So this is GPROM, and when we look at, those boxes, you have the, let's say, real process for each of them. Here's the electrolysis, and here you can optimize every component. You can design the plates of your electrolyzer and so on. This is the in-depth, let's say, modification. You have also the compression, the purification, and so on. And the idea is then to optimize your project and then to transfer all this information to your, let's say, engineering tool in order to go to the next phase of your project. Okay, another topic I would like not to go in, let's say, in depth for the automation, but just want to mention also what we are trying to do here in the automation part, how to facilitate, let's say, the engineering, how to do it faster, how to scale up faster your project. So here we have developed what we call template. It's called technology stack for hydrogen plants, and it's using this modular engineering approach. So the idea is to have, let's say, kind of standard templates for hydrogen plants, for hydrogen project. That could be, let's say, 50, 60 or more % ready for your project. And the idea is to provide that to the different project developer, EPCs. So then they have just little effort to put in their project in order to, let's say, customize that design in order to be implemented in their project. And this design is valid for the, let's say, PNID of your plant, but also for the automation part. They are all linked together. And then we use this digital twin concept in order to achieve that. Of course, this is also possible because we have lots of know-how in the hydrogen sector. My colleague will mention later, but we are also operating a hydrogen plant in Germany. It's called Wunsiedel, but we'll have a few words about that. So we are trying to implement that into project to really reduce the, let's say, engineering cost. And so I've been discussing quite extensively on the, let's say, how we develop projects in the conceptual phase, but also how to simulate different parts of your project. Now we'll let my colleague to discuss a little bit on the operation side. We have a tool called Hydrogen Performance Suite, and then I will invite JP to the stage.
Okay, I'm going to more focus on operation phase in the hydrogen plant. So he's explained about integrated engineering, and so we're going to more focus on the operation. And we explained about integrated engineering so far. from the GPROMs to the automation and the automation twin right before the running the plant. We also can create the automation twin, which is a Sept. So it creates it combined with all the data which is running in the plant through the automation system and the simulation modeling behind. So we can also combine the GPROMs, as I said, and the Sept and the PC7. So what we can do right now, it also creates a different cockpits on the individual demands. And it also make it available within our XHQ, which is a software and the application to have operation intelligence. So we're going to give you some representing slide of our hydrogen performance suite, so-called hydrogen performance suite, and it's able to fleet management and performance monitoring and the energy management system. And this is one of the slides I'm going to explain about overview of hydrogen production plants. And you can see, and we have key process flow and from the electricities to the distribution. And you also have some process characteristic and hydrogen and the performance and also the predictive maintenance. If you have some anomalies detected in the production plants, you can see some exclamation, the mark on this overview, and you don't have to go deep into the automation, episode 7, things like that. So we can find the solution in this one view, and if you have any topic and you want to go deep into the automation, and of course, we can find the solution in automation level as well. And this is also the energy management system. And energy cost is the most major the cost in operation of green hydrogen plants. So energy management is also the crucial part in operation of a hydrogen plant. So we can give you some insight how to run the hydrogen plants, and you see the left side and the forecast, and there is a button and the drop down the button. If you click the button and the forecast, once the forecast is unloaded and putting those kinds of, it's interfaced in the external weather forecast, and putting those data into our simulation modeling, and it can define how much energy you can get from the solar and from the wind for the next day. And also due to the hydrogen demand over there, and we can get a hydrogen demand, depending on the hydrogen demand, and to run the hydrogen plants, how much energy you have to purchase from the national grid. On this slide, you can get the transparency on it to save a lot of cost and OPEX and perspective. So, and the left side and the top side, and there is a button, and it's a capture button, sorry, and there is a optimization button over there, and we also have to have a green certificate, and by using our renewable energy, and it produces green hydrogen. So to minimize using the national grid, and we have to have some insights to run the plant. So if we click the optimization button, and operator can define how to run the plant and how to mix the energy resource between the solar and the wind. And this is another example of hydrogen performance suite, and the electrolyzer itself. Electrolyzer itself is very crucial and crucial apparatus, and it has to be maintained on a regular basis. So it also combined with a simulation modeling behind. So in the right side, you can see the performance curve and the real-time trend over there. And there are a certain amount of electrolyzers to run the plants. And this electrolyzer, how many times in the switch and on and off, and how many days the electrolyzer can run, depending on those kinds of things, and the performance curve is defined. So we can run the hydrogen plants based on this performance curve, and we can see this electrolyzer performance in this slide. And in the middle of, in the performance indicator, there's a lot of important components inside the electrolyzer, and the most important, one of the most important is membrane. Membrane degradation, how to define the membrane degradation, and this is also powerful, and when we use our simulation and the GPROMs, as we said, and GPROMs is also powerful for in designing phase and conceptual design, but also is very powerful to use these GPROMs in the operation and maintenance. And there is a certain amount of library already implemented in the GPROMs, so we can see membrane degradation from this slide, and we can check also the predictive, and the maintenance from this design. And also, we can say the fleet management, and there's electrolyzer. There's a lot of an electrolyzer company already running their electrolyzer in several regions and the various regions. So if you use our fleet management, and you can click those in fleet management, and in some reason, and you can go deep into another slide, and we already presented in the before. And I'm going to show some real-life example, and this is Turn2X, a startup company, and we show, and this case is one of a great Power2X reference we like to address. And Turn2X is a startup, and they built a green hydrogen plant, and but green hydrogen plant is one of the major costs, is, as I said, and the energy cost. So to get economical and renewable energy, and they moved it into Spain and get some economical and energy from the solar farm, and also they add some carbon dioxide, which comes from biogas plants, and by the methanation process, and they create the green methane, and which is CO2 neutral, and they put those in green methane into the natural gas network in Spain. But the startup is very important thing is payoff. They have to have a payoff from the investor. So they now have an off-taker contract from the Germany, from the glass manufacturer, and they now have an off-taker agreement with this glass manufacturer, and now their targeting is to 2030 and Turn2X in the targeting, and the 10% of Germany's natural gas demand is quite ambitious. And from this whole process of the plant, and they use our GMS ecosystem and the GPROMs in simulation process and the conceptual design to the operation, and with our pre-engineered templates in COMOS, and also in the PC7 for the automation. Don't have to, district twin, if we use these kinds of GPROMs COMOS, you don't have to create another district twin. It automatically makes district twin solution. And another example, Funsido, and this is our green hydrogen plant we invested, and we established a joint venture with some other stakeholder and Vun H2, and we're not act as like an EPC, but we we put our share into this project, and as already explained, there is some Siemens financial service. We put on our share into this project, and we built a green hydrogen plants. And this is 8.75 megawatts, and from within our Siemens Energy and PEM electrolyzer is installed, and this is running from the energy mix in the wind and the solar, but the wind is more than solar from this plant. And in summary, and there is a lot of stakeholders in hydrogen economy, and the value chain is very widened. So we like to do, and we like to give them our momentum within our digital hydrogen plants. So no one have ever operated a hydrogen plant previous decades. So we're going to build up, we're going to show our digital twin solution to the investor and to the front-end engineering and the EPC. And we also will consult within our technology provider, and we're going to try to have some momentum from this green hydrogen flow, and this is what we like to address so far. Thank you.
Thank you very much for your presentation. Would you like, yes, ladies and gentlemen, please give them a warm once more. Thank you very much. 네, 자동화와 디지털화를 통해서 안전하고 효율적인 수소 생산을 지원하는 지멘스의 기술에 대해서 함께 들어보셨습니다. 이렇게 5개의 강연 마무리하도록 하겠습니다. 전 세계 수소 산업 리더들이 모여서 최신 기술과 트렌드를 소개하고 또 미래 협력을 도모했습니다. 기후변화에 대응하고 또 에너지 안보를 강화하기 위한 값진 논의의 자리에 양일간 함께해 주신 모든 참석자분들께 감사의 말씀 드리겠습니다. 계속해서 진행되는 H2Meet 2024 전시와 프로그램에도 여러분의 많은 관심 부탁드리겠고요. 이것으로 H2Meet 컨퍼런스 2024 리더스 서밋 모든 순서 마치겠습니다. 함께해 주신 여러분 대단히 고맙습니다.